Good afternoon, everyone. Thanks for coming out to my third talk. And today I'm going to talk about astrobiology and the search for life beyond Earth. I did change my title slightly because I thought the universe would be a bit too arrogant to describe life in the entire universe. So I'm going to focus on our Earth, planets in the solar system, and exoplanets. And I just want to give a very quick review, the one-page kind of philosophical review for my last two lectures. And I said that I talked about the hundreds of exoplanets known. I talked about 5 different techniques. I gave just a few highlights on atmospheres and interiors. And I talked about technology developments for finding more planets in the future. And one of the points I made was that in the exoplanet community, there are a lot of motivated individuals who worked in obscurity for 10 years or more, despite the rest of the community telling them that what they were doing would never be possible. I actually was one of those people. And huge promise for the future is actually based on these achievements of the past 2 decades. So if you're the kind of person who has a crazy interdisciplinary idea, actually astrobiology is the field that will accept you. So that's how I'm going to start out the talk, and let's see where it goes. So here's a picture of astrobiology, an artist's illustration, just showing you planet-forming disks through planets, through molecules. And astrobiology does have a definition of the study of the origin, evolution, and distribution of life in the universe. It's a highly interdisciplinary topic. Some people work within their own topic, like physics or chemistry or biology. Others work in ways that span all of those and more. It's kind of an interesting field because it did get a lot of funding from NASA, which was supposed to motivate people to work together. And the question had always been, is it business as usual for individuals who just wanted to get money for their work, or was there truly interdisciplinary work? And I think that we're really seeing some of both of those. Now I'm going to start out my story with this statue. Does anyone know who this is? A lot of people are nodding their heads, some astronomers. Yeah, it's in Rome. Shout out if you know who it is. It is, it's Bruno. And I really like Bruno because he really stood up for ideas that he believed in that many other people did not. And in exoplanets, we tend to focus, so Bruno was a mathematician, physicist, and a friar. He was burned at the stake by authorities in 1600 after the Roman Inquisition found him guilty of heresy. Now in exoplanets, we like to say he was burned at the stake because he believed in heliocentrism, that the Earth went around the sun, and not that the sun and all the stars and planets went around Earth, but he actually had a lot of other issues. Okay, I'm going to talk about life on Earth and life beyond Earth. So let's start with the search for life on Earth. And this is a little tiny review from the other. But what I'm showing here is a picture of Earth, a real photograph of Earth, the pale blue dot taken from 4 billion miles away by the Voyager 1 spacecraft. And yesterday I talked about how if we could see Earth from afar, we'd like to take a spectrum of it. And for those of you who don't know what a spectrum is, I'm not going to review it now. But what I did say yesterday was if you look at this plot, this is just a normalized reflectance, this is wavelength, these are wavelengths up here. You just have to agree with me that this curve is different from a straight line. If reflected light from Earth compared to the sun was a straight line, we would see no features. Those features are caused by molecules in Earth's atmosphere. And this one here is from the Mars Global Surveyor spacecraft when it was en route to Mars in the 1990s. It looked back at Earth to take what Earth would look like as a pale blue dot. On the other hand, it's not really blue in the infrared. I think it's more red. But there's what Earth would look like, and there are the gases. I'll come back to these molecules in a moment. But what I didn't talk about yesterday was vegetation as a surface biosignature. Here's a picture I took almost 10 years ago in Princeton, New Jersey. You know, I used to think Princeton was really a hot place to live until I visited here. But in the summer, Princeton is incredibly humid. It's so hot and humid. See how the grass is all dead? This is a man-made pond, and you can see the trees all around. What I did was I then took the exact same picture in the infrared. And look how it looks in the infrared. It's the exact same picture in the infrared. You can see where the grass is dead. It's not showing up any color, and where it's alive, it's showing up red. Now this is something that for a time astronomers got really excited about. It's called the red edge. And what it is that if you took a light and shined it at a leaf and measured what came back to you, at visible wavelengths, very little light comes back. You know, plants are dark. If you look at a leaf, it's actually quite dark. But in red, 50% of the light would actually come back to you, not just a few percent that comes back at visible wavelengths. And what this means is that if we could see a little further to the infrared, our world would be a very different place. Things would be bright as snow. The air from planets would just be unbelievable. So astronomers were excited about this. Okay, we're going to turn the volume up here. Astronomers were excited because we thought it could be a feature in the spectrum. It's quite a sharp feature. But it turns out wherever you have plants, you also have clouds, like the Amazon rainforest. And so it gets washed out. It turns out to be about a few percent over the whole planet or less. But I wanted you to just know about it as what we would call a biosignature. on Earth. So on Earth, the biosignatures are oxygen and ozone, we call that the smoking gun, anaerobe, biological but a weak signature. Methane is produced by life, 90% of methane is produced by life, but it also is produced geophysically from mid-ocean ridges. We have the red edge of vegetation. And water vapor, we talked about yesterday, evidence for liquid water, it's a habitability indicator. All life on Earth needs liquid water. And so a basic premise is that we want to find another planet with liquid water. It's very hard to find liquid water, so we will look for water vapor in the atmosphere. On a small rocky planet, water vapor indicates liquid water because the water should be photodissociated by sun or starlight with the hydrogen escaping to space. And the fact that if you have water vapor on a rocky planet, it must have a continuous source for replenishment. So here we're stuck in a world of terracentric biosignatures. And if you were to Google biosignatures under scholars, almost everything you see would be talking about this for exoplanets. So that's the story we have so far. And later in the talk, I'll talk about efforts to go beyond these gases for biosignatures. But one thing from the previous spectrum that I want to emphasize is if we ever get data like this from an exoplanet, this will be one of the best data like ever taken of another exoplanet. This is really great data. You don't even see error bars on here because they're quite small, probably too small to show up. But look how big those features are, and look how many or how few gases are represented there. So when we're thinking about biosignatures, we're not thinking about little vents that emit tiny bits of gas. We're thinking about gases that can be emitted in high enough abundance to fill the atmosphere at some level high enough for detection. Okay, so this summarizes this part of the talk. And now I'm going to move to the search for life on Earth part 2. And just like yesterday, I hope people can ask questions if they're short for clarification, and otherwise we'll have a long discussion period at the end. So I'm a planetary scientist and astrophysicist. But what I do, I'm kind of an armchair, what I call an armchair microbiologist, where I try to extract whatever is useful from microbiology to exoplanets. And I'm going to tell you about some of the things that I find interesting and relevant. So it's not exhaustive in any way, and it's really just looking for things that could be relevant for other planets. So the search for life on Earth part 2, and as it relates to exoplanets, is the search for life in extreme environments. Extremophiles, organisms that not only survive but thrive in extreme environments. And one of my favorite ones are black smokers at the Atlantic seafloor. This is 3 kilometers or 5 kilometers deep on the seafloor, and they're vents that emit, actually, you know why I like them so much? Because they're the only place on Earth where you have superfluid. Water is a superfluid existing naturally. That's at such high temperature for a given pressure that actually it's not quite a liquid, not quite a gas. But that's really just at the center of the black smokers. And the temperature drops rapidly away. You have life living down here that doesn't rely on sunlight in any way. And it's going to be a central theme of my talk, that the light extracts energy from chemical potential energy gradients. I'm going to come back to that in more detail. But I also like these because one of my colleagues has been on Alvin and has got to go really deep in the submersible down to the seafloor and collect material from these black smokers to study it in the lab. So here's another picture showing a tube-worm colony near a black smoker. And the main point is that the bottom part of the food chain, life doesn't rely on the sun. There's life down here that produces methane. Remember I mentioned methane as a biosignature gas. Now there's another thing also that I like about microbiology is how many new discoveries are made all the time. Just a couple of years ago, there was life, photosynthetic life was discovered down at the seafloor near one of these vents. And what's super amazing is that it wasn't using sunlight because it cannot penetrate that deep, but it was actually using geothermal light from these sources. So light in the near infrared. So it's great to know that life can operate in all different ways. The downside of microbiology on Earth is that in some of these extreme environments, like these photosynthesizers down here, their source flux is so low for that radiation that they likely only reproduce once every few years. They're likely very slow operating. And that doesn't help us for exoplanets, because in exoplanets, remember, we need a source flux that's big, because a lot of the atmosphere has to be filled with the gas in order to be detectable from afar. So life that lives in rocks or deep in the ocean that isn't reproducing quickly or isn't metabolizing quickly, it's really not that helpful for exoplanets. Nonetheless, we're inspired by the fact that life exists in many places on Earth. Here's how many people have been to Yellowstone? Oh, quite a lot. This is a hot spring where there's boiling water. When I was out there, they told me that people discovered life out there just by putting a glass slide in boiling water and then picking it up a day later and finding life on that slide. But if you've been here, you'll know that there are signs that say, do not fall in. Because, if you fall in, it actually is completely fatal. When we were there, we had someone in our group who had a story related from a guy from previously who did tell us that something fell in. His dog jumped in, and he jumped in after the dog, and you really don't survive here. So the point to take away about some of these extremophiles is they can thrive in environments that are completely fatal to humans in other life. And this is why we like it for exoplanets, because there are a lot of planets out there that will be completely different from Earth. And here's a nice little slide put out by NASA Astrobiology. They actually, if you teach in astrobiology, they have a bunch of these. And on the back, they have a description of what it is. And it's quite nice. There's a lot of nice ones. I help them out with some for exoplanets. But here, there's just a brief summary of some of the extremophiles. Life in the extremes, ones that like salty places, ones that like acid, ones that like alkali areas, radio-resistant microbes that have been found in Chernobyl nuclear area. Barophiles, one that lives at high pressure. There's ones that can live in dry places. Here's another Yellowstone picture. And ones that live in rocks. And some life actually lives in rocks, and it lives kilometers beneath Earth. So we're inspired by this, because for exoplanets, it means to us that life can live on almost any environment on Earth that has some water. It gives us hope that there is life in any kind of environment we can imagine, given some temperature and liquid constraints. So now I'm going to turn to the kind of chemistry theme, and I'm going to make it as simple as I can. I'm going to start with this apartment building, and with a little story. And the story is that, actually, and some of you probably share this story. There's got to be at least one person here who has the same story. When I was a child, I lived in an apartment building on the 18th floor on weekends with my father. And I think in those days, parents didn't watch their kids as much, because I must have only been about 4, and I had a brother and sister who were 1 year older or younger. And we were on the balcony on the 18th floor, and we would drop stuff off to see what happened. And if I can remember correctly, he lived like overlooking the front of the building, so it probably wasn't a good idea. So he drops stuff off, and the higher you are, things go faster, and they can have more energy by the time they reach the bottom, because your potential energy is higher the higher you go. So I don't know if anyone here did this. Drop stuff off the floor. At least one person. Oh, okay, no. Okay, and then I told this story to a colleague that I worked with, who's a chemist. He said, well, when he was a child, he would set fire to things, because the chemists like chemical reactions. So afterwards, you'll have to tell me what biologists do with it. I know they probably doesn't like things. But that's what the physicist does. You drop things off.